Well, hey gang, I'm glad you're here with me taking notes. Today we're going to talk about finding the factors to those special products that we talked about when we were putting in standard form. There's a very nice pattern when it comes to them. So let's go ahead and take a look at what those patterns are algebraically. Because you know we probably looked at it over algebra tiles today. Alright, the first one is difference of two squares pattern. Okay, that's where that a squared and that b squared are the difference of the same number times the same number. Okay, for example, 3 times 3 is 9, and we'll get into more. Okay, so when we factor it, one's a positive, one's a negative. We looked at this in the reverse way. A couple weeks ago. I think it was 7.4 where we talked about this in the reverse. So here's what we mean. Right here, our a is a perfect square of a 1, because 1 times 1 is 1, and our 36 is a perfect square of 6 times 6. Okay, so when that happens, there's a beautiful pattern we can use. We don't have to use the box and diamond, but you still can. Okay, that this is going to be x minus 6 times x plus 6, and you're done. Okay, this pattern right here only works with a binomial, and then you're trying to factor it. Binomial factored. Okay, this one, we have a perfect square of 1 times 1. We have a perfect square of 10 times 10, and there is that subtraction sign in between them. So we know we can simplify this to 10 plus m times 10 minus m. Big picture, what are you solving for here again? All of these are x-intercepts. Okay, so this one has an x-intercept, number 1, of positive 6 and negative 6. Number 2 has x-intercepts of positive 10 and negative 10. That's the whole point of this. Number 3, we have a perfect one of 3 times 3 and a perfect one of 4 times 4. So that will become 3, can't forget that 3 now, and minus or plus, doesn't matter, 4 times 3 and plus 4. These two signs have to be opposite. Oh, and make sure it says subtraction in the very beginning, otherwise we can't use this. It's not a subtraction. Alright, this next one, okay, we have a perfect square of 4 times 4, a perfect square of 7 times 7, and it says subtraction in between it. So it's going to be 4h plus 7 times 4h minus 7. And there. Didn't even have to use the box and diamond. We could have solved it knowing the fact that this pattern right here exists. Let's go in to our second pattern. This one's called the perfect square trinomial. The other one was a binomial. This one's a trinomial. And we talked about this in the reverse way. So it's when it's the same thing times itself. The same thing times itself. Okay, how are we going to be able to figure that out? That's what we're thinking. We're going to take a look at this example right here. Okay. We know that these two things have a 3 in common. Okay, that's how we're going to look at it. We can rewrite it using our perfect square pattern and then put it into our times itself pattern. Or again, you can still use that box and diamond method. Okay, so we have this m squared. Okay, we know we can rewrite this right here to say negative 2, because it's going to always say times 1 times m plus 1 squared. What's 1 squared? 1. We know that this has to be b, and then we also know that this has to be, one second, this also has to be A. because this 2 right here is a part of that little pattern that it has. So we can rewrite this to say a squared, which is 1m, and then it has a subtraction sign, minus 1 squared. All right, let's try this again. This is an easier way, actually. We know that this one is going to be perfect right here, because 5 times 5, perfect square, is a perfect square. We know that 5 times 2 is 10, okay? And then this is going to be 1 times 1, perfect square, perfect square, perfect square. It says subtraction in between, so we're going to have that minus sign. Here's A, here's B, so D minus, because it says subtraction, 5 squared. Or you can use the box and diamond method. Let's look at example 7. Okay, perfect square of 1 times 1. This would be a perfect square right here of 10 times 10. Okay, now I know 10 times 1 times 2 is 20, so this is that special one, okay? And here's A, Z, says addition between them, plus perfect square 10 squared, and we did it. All right, here is your on your own problems. Please pause your video and try these problems on your own. Resume when you're ready to check your answers. All right, here's what we should have gotten so far. I'd really like to go over 4 and 5 together, because here's the big picture that we want to get to, is solving for x-intercepts. 49 equals 9k squared. We're going to take away 9k squared from both sides, so we can use that zero product property. It will really make life a lot better, okay? So we'll have negative 9k squared plus 49 equals 0. Now we're going to factor. I don't really like the fact that this k squared is negative, so I'm going to flip the signs of everything. Positive k squared minus 49 equals 0. And 0 as a negative is still 0, so we don't worry about that. Okay. Now I'm going to factor it. This is one of those special ones where this is 3 times 3. This one is 7 times 7, so this is going to say 3k plus 7, 3k minus 7 equals 0. So right here, this one, zero product property is k equals negative 7 divided by 3. That's where it's the x-intercept, not a pretty number. And this one is k equals positive 7 divided by 3. All right, you could also write this as k equals plus or minus 7/3. Means the same thing. Number 5, we're going to rewrite it so that it's equal to 0 by adding 64 to both sides. Okay, now we're going to factor it. This is one of those special ones. What times what is 64? 8. Okay, and then what times 8 times 16 is 6. 8 times 2 is 16, and then a 1 is a, so we have right here t minus 8 squared equals 0. Zero product property now, and then t is going to be equal to positive 8. This one only has 1, this one has 2. All right, go ahead and answer that EQ. I hope you're having a great night. Your checkpoint is up and running. Later, gang.